Okay, this video I'm going to talk about syntactic categories. And these are also going to be definable sets. Okay, and so for this discussion, in this discussion, we are going to fix a fragment of logic, of first order logic, and so I'll be thinking about classical things, so the classical fragment where I include all these rules of deductions, and the arguments go through, and there is a multitude of constructions as we will vary this fragment. Okay, so right now I'm going to fix one. You can fix one that's different from mine, and whatever I say is going to still go through for your fragment, but you have to just modify the definition slightly. That's what I'm saying. Okay. Okay, so for example, I'm going to define a syntactic category. Mine's going to be the first order syntactic category. Yours could be the geometric syntactic category or the horn syntactic category if you decided to choose only horn fragments and so on and so forth, okay? Or you know, geometric formula. Okay, that's what I mean by this. That being said, to proceed with this, I need to give a definition. Okay. So so we'll in this discussion we're going to have a fixed signature. So we fix sigma, the set of variables, to give us the language. Okay, so that's just a thing that we do, right? And now what I'm going to do is I'm going to define an equivalence relation on formula and context. So if phi of x and psi of y are formula in context xn and y1 to yn, m with n is equal to m, I'm going to define an equivalence relation. In this equivalence relation, it says that psi of y is equivalent to phi of x if and only if psi of x, okay, let's say one can be obtained from the other, by substitution of variables. Let me give so we're defining this thing, and what is this? Let me give a little notation for this. What this means is that what we mean by this is that psi of y is equal to phi of x, where here, so this notation means these things are kind of supposed to cancel, and this means replace the x's in phi of x with y's. Okay, so that's what this notation means, and so we're looking at just this equivalence class of formula like this, and so this is what this notation means. And the other thing that we'll use is that with these square braces, so this will be the equivalence class of formula in context in context under this equivalence relation, this relation under replacement. Okay, so we have this notation for these things. Now I can okay, so again, this is equivalence under of blah formula in context, where blah is your fragment of logic that we fixed. All right. So now we come to the definition of a syntactic category, and they're like definable sets for a specific theory. So we fix our signature, and then we'll fix, and the variables, I guess. And we fix T, so this is a theory over this, so a collection of sequence. And so we're going to define the syntactic category, and the objects are going to be like definable sets. So this you should think of this as like definable sets before. And then the morphisms, so the objects, are these equivalences of formula. So these are like definable sets. And the morphisms will be definable morphisms. And I'm going to explain what this is. Okay, and so I should say here that here, this is, again, we can do a flavor of this for every fragment of logic that we can, okay? And so what I've defined here is this syntactic category. All right, so let me kind of write down what a morphism is, and then, so what is a morphism? So here, so if we have this guy, and it goes, so I'll write it down first, and then we will explain what the heck these conditions are, and they're actually very geometric conditions. They're pretty simple things. Okay, so here, this is what a morphism is. This guy here is a we can call a tau provable equivalence class of formula in context xy. Okay, and what does this mean? So this means that, two things are equivalent if, the sequent for one implying the other, one proves the other and the other proves it, those are both tau provable. Okay, so they're equivalent under these operations of the proof techniques. Okay, so the axioms for these things, so the conditions, so there's 1, 2, 3 conditions. So one condition is about being in the domain of the function. The other condition is about the other condition is about being the graph of this function being contained in the product, and the third condition is about will be about the it's about being a function, actually. So again, so this is about the domain. This one is about the being. I guess we could call it being a correspondence. And this last condition is about being a function. And let me just write down what they are. So it says that. So this one says the following. We have this statement, so that there exists some y. This one says, so we'll come to this in a second. So I'm going to draw some pictures on the next slide here. Okay, so we have these three sequence. Okay, and then so these are the axioms that they have. Okay, and then we'll have finally we'll have this the composition rule. Okay, so if we have phi of x, so I'm omitting here these. Oh, actually, I'm not omitting here anything. So if we have phi of x, so I think of these as definable sets. And this coincides with what we saw in a previous video about definable sets here. So this is kind of the functor of points viewpoint that I talked about before. So this is alpha xy. This is beta of yz. Then this composition, which we can call gamma of yz. So I guess technically I should put parentheses around all these things. I am so close to omitting them because they're so annoying that gamma, oh sorry, this is gamma of xc. Gamma of xc is that there exists some y where you have theta of xy and alpha of xy and beta of yz. Okay, so this is the rule for composition, and then we have this rule for the identity, and the identity thing says that if I have phi of x here, the identity is going. So okay, bear with me for a moment. Okay. So this is going to be it's a little painful, right? To just kind of like, write all these down like this without any motivation, but now I promise you here's the motivation. Okay, so let's think of this geometrically, and let's look at each formula kind of as geometric objects. So this is here. I'm just going to use different notation. So this z is equal to theta of xy. Okay, sorry, this is not theta, this is, let's do this, let's call this gamma is theta of xy, like this. Okay, so we have two things. This is going to be the morphism here, and the picture is the following. It's like this. Here's x-axis, here's the y-axis, and then we have something that's cut out by another formula that's in here, and this is what gamma is. So now we can start to look at each of the separate formula. Okay, so here's the first formula here. This. Okay, and when we look at this formula and we look at what we know now about what this entailment means in terms of, or what the sequent means in terms, how do we interpret this sequent in categories and whether or not it's true? Well, this thing here, we know that the existential quantifier now is a projection. So this thing, maybe I should have written, maybe I shouldn't have, drawn this thing. Okay, so the way that I drew it is the domain is everywhere, but suppose, that it doesn't land everywhere, so we could have, this thing, this could be the image. So this image that I'm drawing, this blue image, is that there exists some y of theta of xy. Okay, and what it does is it looks for images up here. So this is the image of this crap down here, and okay, and what this is saying is that the formula for phi, this formula here, is is lying. So this is phi of x. So this is the definable set here. So it's saying that x is contained in the projection of. So x is completely contained in this projection here, down onto this axis. Okay, so maybe I shouldn't have written it as x. I should have written it as So yeah, I shouldn't have written this as x. I should have written this as, you know, the one copy of affine space. AN. This is AM or something. Okay, and so AM is down here, or AN. And then here, so this is the x-axis, and this is the y-axis. And then x is the green stuff. So this stuff here is all, this is all x. Okay, and so what the formula actually says is that when you project this down, x is contained in all this crap. Okay, so that's what the first formula says. The second formula says essentially, so let's look at the second formula. So the second formula, that's this one here. It says that it says that this function here is contained in these two parts. Okay, so again, let's draw this picture. So we'll have so I'll draw it in a certain way. So here's x. Here I'm going to draw y as two-dimensional. Here's here's the this is not x. Okay, this is going to be y. And then within x, we're just going to take two dots here. Okay, so this is a copy of A2. So these are the two coordinates that are determining that y is cut out of. And then this is a single coordinate. This is A1 here. Okay. And, okay, so so gamma is going to live inside A3, which is the product of these two things. And we can draw the product of these two things. Okay, so this is the product of these two things. And so if I were going to, in this product here, so this is the y coordinate, and this is the x coordinate down here. And, okay, so here, okay, so maybe this is, this is the x coordinate. These are really two coordinates here. So this accounts for two directions. Okay, and this is one direction, like the band. And here, again, we forget about all the other directions but the x-axis. So the fiber of this projection here, so we have this projection and we have a projection here. The fiber of this projection, so if I take these points, looks like this. This plane here and then this one, something like this plane here. Okay? The fiber of this projection, this guy here, okay, so this is everything lying above one of these lines. So it's like we could take, I don't know, something like this. We have this line down here, and then it's this whole blue plane cutting here. Okay, so we have this whole blue plane thing, and then yeah. Okay, so this thing goes this way, and we have these two things, and then when we intersect them, we get this green bit here. Okay, so these are these two green lines. Okay, and so let's remind ourselves what y is. So y was this psi of y. Okay, x was this phi of x. This lived inside one coordinate line, but we had this one condition written down. These were these other conditions. And okay, so when we look at what this single condition looks like inside this 3 space here. So this single condition, okay, so this is the condition phi of x here. These are these two lines, or these two planes here. So this is in the context x, y. Okay, so this is in a different context, so we've gotten rid of it. And then again, the blue part here, so this is psi of y in more of a context, in the context y. Okay, so it's kind of like if in 3 space, you know, if you, or like a, so okay, so in 2-dimensional space, you can draw like an R2, you can have the equation for a line. It's like y is equal to mx plus b. But if you view this in 3-dimensional space, it now cuts out a plane, and this is exactly what this picture is. Okay, so now what I've drawn in green here is the condition you know, what I've drawn in green is this formula here in the context x, y. So, okay, and you can see that this thing here is just x cross y. So this is what this is. So, okay, and then if we look at what entailment says, okay, so we look at this formula here. So now let's do it in a light blue, and then we do this one here. So this formula here, this dude. What this is saying is that this graph is contained in the product. So the blue formula says that gamma, which is this dude here, is contained in the product of these two varieties. And this is what you expect if you were going to do if you go back to the original, when you first learned what a function was you know, a special type of relation, and relations were subsets of products. Okay, and that's exactly what it's saying. That's what the second condition says. Okay, so we've done the first two, and now I'll do this one in blue again. We can look at this formula here. And the third one, the third condition is quite simple, actually. So the third condition is you think of this theta of x, y. And if, again, we want it to be viewed as a function, so let's think about it as, so this is here, we'll think about it as, well, I'll just write it as equals, but I should put it in quotes. So this is y is equal to f of x for some function. Okay, and so now let's write out what this formula says. Okay, so it says that if so what did it say? It said that let's go back here. If we have these two xy and xz, then y is z. Okay, so this says theta of xy. Sorry, theta of xy and theta of xz. Okay, so let's write what this says. And then we'll write down the conclusion over here. So we'll write it like this. So the conclusion, so this is the prove arrow. So the conclusion was y is equal to z. So if these two formulas hold, so what is this saying? So this is really saying, this formula here is really saying that y is equal to f of x. And z is equal to f of x. Oh, so this is just a statement that says that it's a unique output. All right, and so this formula, so the formula, the third condition, is really saying that, you know, theta is actually a function. a function. Okay, it doesn't, I mean, the other thing is about this containment, but it's the same thing about what we were saying before. So the places where they're equal is contained in this part where these two relations are equal, okay? So in particular, yeah, they're equal. Okay, so that's very nice. So for one input, there's one output. Okay, so again, this is what it says. This one talks about the domain of the function. This one talks about the graph, this actually being a graph of the function, meaning it lives where it's supposed to live. And then this is about being a function property. Okay? So, okay. And that's what these formulas are actually saying, geometrically. Yeah, and that's how we should think about them. Okay, yeah, maybe we can talk about the composition law here. So I'll just say something really quick about this part here, and I'll do it on the same, maybe if I have space, I'll do it on the same slide here. Okay, so what it was saying is that if we have, well, I guess I don't have space. So if we have two guys, and let's say beta of yz, and so there exists a y, so this was equal to the composition of functions, so this is xz. Okay, so let's write this down in that other notation that we were talking about. So what this is saying is that, so we should think about this, this is saying that y is equal to f of x, and let's say z is equal to g of y. So that's what this formula is. So there exists some y such that y is the output of this guy and z is the output of the next guy. Okay, well, that makes sense. And this is by uniqueness. So by uniqueness, of the outputs of functions, this makes sense. This is what we expect for composition of functions. Okay, that's all. Is that all I want to say? Okay, so this is actually what the definition of a syntactic category is. So a syntactic category is this dude here, okay, where the objects are these kind of equivalence classes. So these are the definable sets. Okay, so this is why I was calling this definable sets. These are definable sets. Okay, and then these are definable morphisms. Okay, and definable morphisms are these things. So they satisfy the properties of a function. All right. So I forgot to do one of the kind of the fun parts. The fruits of the labor is defining models of theories. So so let's take a definition. So we will say that, let's fix everything. Sigma be a signature. Let M be a sigma structure in some category C. Okay, and then we'll say that, so suppose phi psi and phi in L sigma have a shared context X, with sort A. Okay, and then this could be a tuple, and this could be a tuple here. Then we'll say that at M M models the deduction phi implies psi, and right, so M models this deduction if and only if, and we defined this before, so that this thing psi M, and so this is true. Okay, so I mean I guess I don't need to write that, but and remember that this is this thing means this formula here means that psi of x is less than or equal to of M. So this is this object, and we have phi of x of M in the sub-objects here of this category where we take a to the m. Okay, so this is the sort of the x variables. So M models this formula, so this formula, this thing will be true if we have this containment here. Okay, and so also for this definition, we need C to have enough structure to be able to interpret / define the formula. Okay, so that's kind of warning here. So this is what we need. Okay, so this is what it means to be model a formula. Definition. So let T a subset of the set of all deductions so everything like this. Let's say psi. Let's do it this way this time. So these are all these things. So we take some theory and some signature with some variables. Okay, so we have this language, and we have the subset. So we see that M. Okay, so we also need to take. Let me just define everything. M is going to be a structure for this category, and again we suppose all formula are interpretable in the category C. Okay, so we have this theory, we have our structure, we said that our formulas are interpretable, and now we can make the definition that M is a model of T, and then this thing is and then this is the same thing as writing this symbol. So this is writing if and only if M proves, and then we have some formula P. So this is maybe this one of these deductions for all P and T. Okay, so this is what it means to be modeled. A model, okay? And so that's cool. So now we can define the category. So definition. So T of C this is the category of models of T valued in the category. And so this is just the subcategory of structures which are just models in T. So this is the subcategory. Okay, so this is the category of models valued in T. So this is how we define a model of a theory with values in a category. So this kind of gets interesting because if you take the theory of groups and you take C to be topological spaces, then the models that you get are topological groups. So this is the kind of thing that happens. And then you can kind of go blue in the face with that idea. So there's kind of an interesting fact, and what now I'm driving at is a different type of morphism for models. So, but let me just first give you a fact: is that if phi, let's do something. So let phi of x be a formula in context for x. Xn, and let's say that the sort of x is A, and this is really a product of AI, it's a bunch of other sorts. Okay, and then, so we have this formula in context here. If phi is geometric, so is geometric, and let's say h from m to n is a morphism in the category of structures with values in C, then we have the following commutative diagram. So there exists a diagram like this. So we can interpret this in M. It's a subobject of A to the M. Okay. Then there's this H of A. So this is the functor that's induced by the morphism of structures here to N. And we have this phi of x to the N. Okay. Okay, this is important. This is crucial. This is not true. This is not true if the formula is not geometric. And remember, geometric, for example, you're not allowed to, in general, okay, so this has for all quantifiers. Okay, so this is kind of interesting. So I mean, you're not allowed to have for all quantifiers, right? So you can have infinite disjunction, excuse me, you can have infinite disjunction, but you can't have for all quantifiers. Yeah, so, okay, so let me just say what the proof idea is. The proof idea, and most of them are, and then I'll put a reference in the bottom. The proof idea is that is induction on how you build formula. On how the formulas are built. Plus, the properties of C. So I guess C needs to be a geometric category in order to interpret a geometric formula. Okay. Okay. That being said, because these don't always commute, we're going to create a new type of morphism between models. Okay. So definition. So let M and N, an element of be models for a theory with values in a category. And then we're going to take a morphism of these things, Biomorphism. So this is just a morphism of structures. We say that F is elementary provided the diagram, so provided for every first order formula, every first order formula. Okay, I'm not defining every, of course, but I'm just saying that's emphasis on every. For every first order formula phi of x in context x with sort A, the diagram, the induced diagram, and then I'm going to write down the diagram. This thing M, A of M, A of N, so this whole thing commutes. Let's say, let me just write it in the diagram, blah, comma, commutes. Okay, and so this is what an elementary morphism is for models. And so, or maybe I should have called this model, not models, but okay, you guys know what I meant. And so definition, so this is maybe a notation, model, and then we're going to put a subscript E here of T with values in C. So this is going to be okay, so this is going to be the category of T models in C with elementary morphisms, elementary embeddings as morphisms. So this is an important thing. This is really confusing to me, actually, the first time so I guess it's because of this fact here that this thing doesn't really hold, that why we're actually working with elementary embeddings instead of all random, morphisms with structures off the street. And so this is why the model theorists use this. Okay, so I just want to note the following, so that if, let's say that we have some structures, and then we have M and N in, let's say, sigma structures valued in sets, and we have a morphism of them, so this will be a map of sets. Then, so I'm going to assume it's one sorted. Then, if H is elementary, then H is injective. Okay, and so the idea. So proof idea. So this follows from the commutativity, or the pullback property of commutative diagrams, of the commutative diagrams. For morphisms of structures, or let's say for definable sets. And so this is a necessary condition. So to give a non-example, so a non-example of an elementary embedding, so if sigma is a ring structure, so that this is for commutative rings, so this is plus times minus 0, 1, then and so let's take T to be the theory of rings. So in this situation, any non-injective ring homomorphism is a non-elementary embedding. So there are more complicated examples. For example, there's this Tarski-Seidenberg theorem, where for real closed fields. And so some of these theorems about elementary embeddings are quite complicated. So so let me say that here's a complicated version of an elementary complicated example, which I'm not going to prove. Okay, so in the structure uh, 0, 1 plus times less than or equal to the map, so the algebraic real numbers is elementary. Okay, so this is what allows us to do. So okay, so this is one of the big parts of this Tarski-Seidenberg. So by the way, so this says that if you take the theory of the reals, so the theory of something is the set of all formula which are true in this structure. So this is with the signature sigma is equal to 0, 1 plus times this as above, has quantifier elimination. Okay, so this is a theorem, and what this says is that every definable set here is actually equivalent to a definable set where the formula for the definable set doesn't have any quantifiers in it. And so this lets you to prove interesting things. So an interesting consequence while I'm here is something like, so that the image of a semi-algebraic set of, let's say, R cross R. So this is something formulated in this language. And if we project it down, let's say cross R, we project it down to, say, R2 is algebraic, or is semi-algebraic. So if you take a semi-algebraic subset of R3 and you project it down to R2, it'll remain algebraic. So under these projection maps. So this is kind of like a Chevalier theorem. And so this says that the image of a constructible set in algebraic geometry. This says that the image of a constructible set is constructible. Okay, so that's all I wanted to say about this.